So in this problem, we are told that there's a scuba diver, and the total volume of the salt water displaced by the scuba diver is 67 liters, and this includes her scuba gear. And the mass of the total system of her body weight and the scuba gear is going to be 70.4 kilograms. We're told that the density of salt water is 1,025 kilograms per cubic meter, and we are asked to determine what is the buoyant force and will she sink and float? Okay, so to start this question, we have to ask, okay, what is the force of buoyancy here? Well, we know that the force of buoyancy is always equal to, this will be the density of the fluid that you're in times the volume displaced. So how much of that water did you displace, or any fluid really? And then, so we have the density of the fluid, the volume that we displaced, and then we have to times it by gravity, right? Because these two terms will cancel meters cubed, leaving us with kilograms. Then we have to multiply that by meters per second to get a force of newtons. Okay, so that's the force of buoyancy. And notice how I said the volume was in meters squared. And we're given the volume in liters. That is not good. But there is a trick that you can use throughout your entire chemistry or physics career to really be able to convert liters to meters if you need to, or to cubic meters. And it's the idea that 1 centimeter cubed is equal to 1 milliliter. Okay, so let's just do a simple conversion here. 67 liters, okay, is how many milliliters? Well, we take 1 liter, and we times it by 1,000 milliliters. Okay, so we have 67 liters times 1,000 milliliters. Okay, and there's this idea, and you might have learned it, and if you didn't, that's okay. Now you're going to learn it, how to do the simple conversion from liters to cubic meters, right? So we're going to say that 1 milliliter is equal to 1 cubic centimeter. Okay, this is very important. This is the bridge that you might not know. 1 cubic centimeter is equal to a milliliter. That's just a standard conversion that just happens to work, right? Probably some weird story behind that. I'd look that up if I were you. But given that we can make this conversion, now it's simple. Now we can convert to cubic meters. That's what we need, right? Cubic meters is going to be equal to 100 centimeters cubed. Now, very, very, very important here. When we do this conversion, right, from cubic centimeters to meters squared, it's not just a dividing by 100, it's dividing by 100 cubed. Now you might look at that and you're like, what? That makes no sense, right? It's in a cubic meter. Why do we have to do the conversion? Well, to answer this, I kind of just want to give you just a simple explanation that you can either understand, or if you don't understand, that's okay, we'll move on. So when we convert from just meters to say like centimeters, it's a direct 100 because we know that for every meter there's 100 centimeters, right? So if this stick is 1 meter long, we know that there's 100 subunits of 1 centimeters. Okay, fair enough. But when we go from a 1 cubic meter to a cubic centimeter, it's not just an 100, right? So there's a x, a y, and a z component, right? So I'll actually write this out, y, x, z, okay? X being vertical, y being horizontal, z being going out of the plane directly perpendicular to the horizontal component. So it's not just 100 centimeters here, right? If this is 1 meter, right, a cubic meter encapsulates that entire volume, right? It's going to encapsulate all of that volume encapsulated in that 3D vector, right? So there's 100, and we know that volume is length with height, right? Length with height, it's not just 100. There's not 100 subunits here. Well, there is in just the horizontal, but it's also this and also this. And that's 100 times 100 times 100, which is 100 cubed. Okay, Hopefully that made sense, maybe not, but that's the way I like to think about it is, okay, it's a 3D space. It's not a linear one-dimensional space that we're making a conversion in. All that just to find volume, guys. Holy crap. When I did this calculation, I didn't think about that, right? And it made me realize and learn that you have to multiply that by a cube, a cubic factor. So let's just plug and chug the calculation. Divided by 100 to the third. We're gonna find that our volume is 0.067 cubic meters. Okay, so a liter is not equal to a cubic meter. So it turns out we get this here. Okay, so now that we actually have the correct units for the volume of the fluid displaced, now we can solve for the force of buoyancy. So let's go ahead and do that. So we'll say F of B is equal to the density of the fluid. Now, this wasn't given directly in the problem, at least from where I got it. You have to actually look at the textbook for this, right? If you say 1,000, because of that's just normal water, you're gonna get the problem wrong, which is kind of a little bit of bullshit, but you know, that's how these online textbooks work now, right? Who cares about getting a physical textbook? I'm ranting. I need to shut up. And then 9.81 meters a second. Okay, so that's what we got there. That's our equation. We have our density of the fluid, volume displaced, and the gravity. Okay, so now let's solve for the force of buoyancy times 0.067 times 9.81. The force of buoyancy is going to be equal to 674 newtons. So there's a force of buoyancy working 674 newtons in the positive y direction. But then we're asked, is that force of buoyancy enough to help the diver sink or float? What's going to happen? Well, to answer this question, we need to first understand the overall forces acting on the diver. So I'll represent, oh man, this marker just died on me. To the trash can. Wham. Okay, so if we represent this diver as a cube, what are the forces acting on it? Well, we found the force of buoyancy to be acting this way, but that's not the only force. Remember, even though we're in a fluid, mass times gravity still exists. That's why heavy objects sink in the water, right? Because it's not just that they're falling. Well, you think through the air, you know, that you can fall through the air, but you can't fall through fluid, you just sink. But it's the same thing causing you to sink or fall through the air or sink through the water. It's mass times gravity, that attraction that you have towards the earth, right? So let's go ahead and solve for this. Okay, how do we solve that? Well, it's just mass times gravity. So the total mass, and this is where the mass total comes in handy. The system of the scuba diver and her gear is 70.4 kilograms, times that by gravity. We're going to get that the downwards force is 691 newtons rounded. And we said that the force of buoyancy is 672 newtons. Well, there's a differential here, and what's the net movement? If there's two forces acting on each other, who's going to win? Who's going to win? What's the higher number? That's going to be mass times gravity. So she is going to, unfortunately, sink in this case. Unless she applies like a swimming force and she swims through the water, she'll be able to go up. But she's just not going to float naturally. Hope you guys enjoyed. If you did, please like and subscribe. I would greatly appreciate it. If you have any questions, put a comment down below. I would love to answer your questions. Have a wonderful day, guys.